All right, so what we're going to look at today is a new application of integration. And as usual, we're going to start by kind of figuring it out by writing down, why do I still have this thing on? I just came from class, sorry about that. We're going to start by writing down an approximation of something in terms of a sum. Then what we're going to do is, as we approximate this better and better, we'll see, well, actually, this sum is really kind of a Riemann sum, and therefore it can be interpreted as an integral. Okay, this is like standard operating procedure from before. If you think back to what we've done with other applications of integration, that's kind of where we got everything from. We would approximate something with a sum. In the limit, it turns into an integral. And what we're going to approximate today is arc length. So what is arc length? Well, in one sense, arc length is what we're about to figure out now. But intuitively, what we want arc length to be is we want it to be the length of a curve between 2 points. However, the problem, of course, is that if the curve is not a straight line, that may be something rather complicated. But let's start out with the easy case. What if we have just a straight line? Well, in the case of a straight line, then the distance is going to be the square root of delta x squared plus delta y squared. So that is actually not too bad to do. And this, of course, is just the Pythagorean theorem. So that's where that comes from. Now, here's what we're going to do. Suppose that I've got some kind of a non-straight curve. So we have some sort of arbitrary curve going between 2 points. So maybe here's my point A and point B where things are going to start and end. We're going along like this. Let's suppose that this is y equals f of x, although we're actually not going to write it down with that notation really here. What can we write down in order to approximate this thing? Well, here's what we can do. We can break this thing apart into pieces. And when we break this thing apart into pieces, what I'm going to do is on each piece, I'm going to put a straight line. So let's see if I have another color here that I can do this with. Hopefully that shows up a little bit on the camera okay. I can approximate this with straight lines. And then what is going to be the distance for each one of these straight lines? Well, it's going to be the change in x squared plus the change in y squared. And so what we're going to do is we're going to say, okay, so let's, denote each of these things as this is going to be delta x1, that's not a delta, delta y1, and then we're going to have delta x2, delta y2, and so on. So we have a bunch of these changes in x's and changes in y's. Each one corresponds to one of these pieces of the straight lines that we have used. And so our approximate length is going to be the sum over all of the pieces of square root delta xi squared plus delta yi squared. Now, there's two different ways that I can go at this point. And I'm going to show you the one for x's. So let's suppose that we fix all the delta xi's to be equal to one fixed delta x. In other words, we take the intervals to be equally spaced along the x variable. The other thing I could do is I could maybe do the same thing along the y variable, but we'll look at that in a moment because it's pretty much identical. Like there's literally not much of a change here, except that we are kind of doing this in the with the variables switched. So in that case, this is going to be the sum, I equals 1 up to n, of the square root of delta x squared plus delta yi squared. And I can rewrite this as the sum from I equals 1 up to n of the square root of 1 plus delta yi divided by delta x squared, and then all multiplied by delta x on the outside. So I factored out a delta x here. Now, the reason I want to do this is because now what's going to happen is this looks like a Riemann sum. So the problem with our original sum is it doesn't look like a Riemann sum. A Riemann sum has to be some quantity times a delta x or a delta y or something like that. It's got to have some kind of a multiplication by the change in the variable. This original thing doesn't have that. But if I factor out the delta x in this way, now I do have it. So now this is a Riemann sum. But it's not quite as simple a Riemann sum as we've seen before. And the reason is because we're not simply calculating, we're not just evaluating a function at a given point. We're actually evaluating the change in a function. So what's going to happen in the limit as the change goes to 0? Well, the good news is we know exactly what that is, because what happens to the limit of delta y over delta x as delta x goes to 0? That's just the derivative. Think all the way back to calculus 1 stuff. The limit as delta x goes to 0 of delta y over delta x, this is dy by dx. That's all it is, okay? So actually, although this is a little bit more of a complicated Riemann sum than we're used to dealing with, in the limit, it actually turns out to be something very familiar to us. And so here's what we get as we take the limit of these Riemann sums. So the limit as delta x goes to 0 of the sum from I equals 1 up to n square root 1 plus delta yi over delta x squared, all multiplied by delta x. And let me put a little line there to emphasize this is something separate. This limit is going to be the integral from a to b of the square root of 1 plus dy dx squared dx, because that's just what these Riemann sums converge to. The only new thing, the thing that we have that's different than it was before, is this time this delta y over delta x term, technically it's a delta yi, but it's basically change in y per change in x. That, in this limit, is going to become the derivative of y with respect to x. So if I have some kind of a formula where I can say, okay, on this curve, y is given as a function of x, I can write down the integral for the arc length in this way. But I could also have done it the opposite way. I could have said, well, what if we take delta y's as the fixed length and we turn the delta x's into the dependent difference? Well, in that case, we would have gotten almost the same thing, except we would have had the sum from I equals 1 up to n square root delta x over delta y, delta xi over delta y squared plus 1 times delta y. And this would approach the integral from a up to b, square root of dx by dy squared plus 1 dy. Okay, so almost exactly the same thing, except the variables have been swapped here. We've swapped the x's and the y's. But our argument is pretty much identical. That's why I really blew through this argument with y's really fast, because it's exactly the same argument. Just take your x's and your y's and swap them. So what I can say then is we actually have these two different formulas here that we can use in order to find these arc lengths. And which one you want to use is going to kind of depend upon the problem at hand. So in some problems, it might be easier to use one versus another. And it partly depends upon, is it easier to write down y as a function of x? Is it easier to write down x as a function of y? All sorts of things like that, okay? So depending upon which one you want to do, you just got to calculate which one of these it is. So for one of them, you have to be able to easily find dy by dx. For the other, you want to be able to find dx by dy. Now, good news, bad news situation here. The good news is that, hey, we have this great formula for calculating arc lengths. The bad news, and it's kind of really bad news in a certain sense, this is a really tricky integral to do in a lot of cases. That's why we've saved this application of integration to this point in our class, where we've now studied like all the methods of finding antiderivatives that we can. Because honestly, finding these antiderivatives, it often requires a lot of cleverness. You often end up having to do a trig substitution. Sometimes you have to do other kinds of substitutions in the process. Sometimes it's just like, it can become just a royal pain. In fact, a lot of times you're going to end up with stuff that you cannot do exactly, okay? So this is why we didn't say this, like this wasn't one of our first examples of applications of integration. Now you'd think, oh, finding arc lengths, that's like a really important thing in terms of applications, because often we have some kind of a curve and we need to know the distance along it, right? Like we have a road, we want to know how long is this road. Well, yeah, it's an important thing, but to ever actually solve one of these integrals is going to take all of those chapter 7 techniques that we've been covering for the past, 2 weeks or something? So that's why we've saved this until this point. So what I want to do here is I want to just write down a few examples of this stuff, and we're not going to solve the integrals. We're just going to write down the integrals and say, okay, this is the integral that gives you the arc length. And then we'll kind of see, oh, and actually this integral is terrible and nobody would ever in their right mind want to try to solve it. But if we had to, we could, because we know how. We do know how to solve a lot of these integrals now. But to start with, let's just write down the integrals and see what we get. So, what we can do in terms of writing down integrals, let's suppose that we want to find the arc length of, let's say, square root of x from x equals 1 to x equals 4. Now, I want to actually show you that there are two different ways of doing this. Actually, before I do that, I should write down more precisely, we want the curve y equals square root x, because the arc length of square root of x, that doesn't entirely make sense. The arc length of this graph, the graph is a curve, that does make sense. So the first problem I wrote down was kind of sloppily written, where it wasn't quite precisely stating what we were looking for. Okay, so what we're going to do here is we're going to say, well, dy by dx is equal to the derivative of x to the 1/2, which is going to be 1/2 x to the minus 1/2. And our arc length is going to be the integral from 1 up to 4, square root of 1 plus 1/2 x to the minus 1/2 squared dx. And this is going to become the integral from 1 up to 4 of the square root of 1 plus 1 over 4x dx. So there we go. We've got this integral written down. Now, how would you solve that? Well, it would take me a minute to figure out the solutions to this thing. You would have to end up doing some weird kinds of substitutions here, honestly, to make this thing work out. I think eventually we could get it, but it would take us a bit of work. See, the problem with all of these arc length things is you end up with these integrals of something ugly under a square root. And it might sound a bit strange for somebody to put it that way, But let's be honest, that's what you generally end up with, is something ugly under a square root. And because of that, these integrals are usually pretty nasty. So that's why, at least for these first few examples, I'd like to sort of just write down the integral and say, let's not worry about solving these things. We spend a lot of time worrying about solving these in chapter 7. We do want to be able to solve these, but for now, let's just practice writing down what the integrals are. Now, I want to notice here that we could have done this in another way as well, because notice that this is the same as doing the arc length of x equals y squared from y equals 1 to y equals 2. So maybe we want to do the arc length this way instead. Could this be any easier? Well, in a sense, sort of. I mean, it's not entirely easier, but it's not entirely more difficult. In fact, it's probably a little bit easier. Why do I think this is going to be a slightly easier way? Well, let's see what we end up with when we write this down. If I write dx by dy, that's dx by dx. There is a y, like I meant to write. What is this going to come out to be? Well, this is going to be 2 times y. Okay, that's nice. But what does that give me with my arc length? I'm going to get the integral from y equals 1 up to 2, square root of 2y squared plus 1 dy. Now, what I want to observe here, this is a much, much nicer integral. Why is it a nicer integral? At least I think it's a nicer integral. I didn't spend a lot of time thinking about that previous integral that we got, but I'm pretty sure it's a mess. Why is this a nice integral? Well, look at this thing. This is just perfect for a trig substitution, right? If I do a trig substitution, tangent theta is equal to 2y, this is going to be exactly perfect for a trig substitution. So, the moral of this story, the moral of these examples, is that you want to be able to write down the arc length in using both of the different formulas that we did, okay? Because sometimes one formula is going to be a total mess, and the other formula may turn out to be something. It's still probably going to be a mess, because you're always going to get kind of a mess, but it's hopefully going to be something that's going to be like more doable. Like in this case, this is almost an immediate trig substitution. This is as close as we can get to a simple trig substitution problem as it comes, just about. I mean, there's probably slightly easier trig substitutions, but this one's very straightforward. Whereas the previous example, or the previous method of solving this example, if I just started with the problem as given and did it as given, well, that turns into a real mess. And the reason is because we end up with the variable in the denominator inside of that thing, inside the square root. I think what we would probably end up wanting to do in that example was actually to do a bunch of algebraic simplification before we tried doing a substitution. But again, what I wanted to show you with this is actually, just by changing over to the other formula, I've made this into a not easy, but at least relatively familiar kind of problem that we can just solve. Okay, so again, I will leave it to you at this point if you want to go through and finish this off, because this is the sort of thing that hopefully you've gotten a lot of practice with. If you run into trouble, let me know, but hopefully you've got a lot of practice with this at this point and you're comfortable just doing this trig substitution. The previous form of this integral, yeah, that was quite the annoying little thing. So if you want to try to work that out, I invite you to do it, but it's probably going to be quite challenging. I haven't done the details of it myself. Okay, so let's write down some other examples. And once again, we'll see that they can kind of be not so nice. So maybe we want to do the arc length of y equals e to the x from x equals 0 to x equals 1. Well, this is going to be dy by dx is still equal to e to the x. So this is just the integral from 0 up to 1. I'm getting my bounds mixed up here. Also, I'm writing it 2. Wow, that was amazing. I just made every mistake it's possible to make just about writing down those bounds. There we go. The integral from 0 up to 1, square root of 1 plus e to the x squared dx, and this is going to become the integral from 0 up to 1 of the square root of 1 plus e to the 2x dx. Now, here's something I'm going to tell you right now. When you're doing these problems on your homeworks and stuff, I really recommend that you keep a table of integrals. I don't know how other professors feel about it, but my feeling is that it's okay to use tables of integrals to solve these types of problems. There are some problems where you're specifically asked to work it out, using trig substitutions, using various techniques, and you want to be able to do that. You do want to be able to do that, but the truth is that out there, when you're actually trying to do one of these problems in practice, you're going to just look it up in a trig integral table or something like that. And I know this in part because, my PhD is in mathematics, but as an undergraduate, I double majored in physics and mathematics. And in physics, we had a tremendous number of really ugly integrals that we had to deal with in our physics courses. Particularly, our advanced physics courses were all kinds of crazy integrals showing up all over the place. But we almost always would just write them in a form where we could look them up in an integral table. Because why kind of reinvent the wheel? You want to understand how people came up with that integral table. But once you understand that, it's okay to just use that table and look up the answers. At least that's sort of my attitude on the matter. Now, some professors might be real sticklers and be like, no, I have to work it out by hand every single time. And my thought is, I want you to know how to work it out by hand, but I don't want you to spend 20 minutes working every problem by hand. Once you're comfortable doing it, it's okay to look things up when you get to something. So once again, this is not exactly an easy integral to do, but we can probably mess around and try to find it. Anyway, for this, I'm just showing you examples of writing it down. Now, there's another way of doing this problem once again, because you'll notice that this is equivalent to asking the question, x equals log y from y equals 0 to y equals e. In other words, this, if I write dx by dy, then is going to be 1 over absolute value of y. And so this would become the integral from 0 up to e, square root of 1 over y squared plus 1 dy. Now, is this any better? Not really. I mean, it's still kind of an annoying integral to do. Plus, we have to turn it into an improper integral because there's diverging stuff here going on. But it is another way of doing it. So maybe you write it in this form. Maybe that's slightly easier to deal with. Who knows? You come up with something that's going to work for you, hopefully, and use that. I'm also going to tell you this. For some applications in the real world, it's okay to just have a decimal approximation. So, you go ahead and you find your integral, but then you just ask a computer to give you a numerical approximation and you call that good enough. Okay, so it's perfectly fine to do that in some applications. But as I've discussed before, it is important to be able to get exact answers because sometimes we need that exactness. Mathematicians need it. Physicists need it. Even other people sometimes need it because, once again, if you take your answer and you then use it for something else, errors snowball very quickly. So approximations that were perfectly serviceably good enough at one step might become way beyond tolerances 5 steps down the road, 10 steps down the road. So depending upon what we are doing, we may need to be able to solve these things exactly. Let's take a look at another example here. Let's suppose that we want to find the arc length of, let's say, x squared plus x. Oh, once again, y equals x squared from x plus x from x equals 2 to x equals 3. Well, this is going to be, we write down y prime is 2x plus 1. So this is going to be the integral from 2 up to 3, square root 2x plus 1 squared plus 1 dx. Now, in this case, when you do this problem, it looks to me like this is a very easy problem to just solve by doing a substitution. Tangent theta is equal to 2x plus 1. Okay, so this is one where we probably want to do it this way. If I tried to solve for x in terms of y, that would become really ugly. I don't actually know how I would solve. Well, I mean, we could work it out, right? But I don't want to solve for x in terms of y here. It would become this really nasty looking thing. Whereas if I have y in terms of x like this, this isn't great, but it's not too bad. It's literally just a trig substitution that we have to do. So, you know, in this case, I'm not even going to bother showing you how you would do it if we solve for x in terms of y, because when we see that this integral is something reasonably doable, we should jump on that and do it. Okay, don't spend a bunch of time trying the other way if the first way that you get it is reasonably nice. Let me see here. So let's take a look at an example that we are going to work out here. Give me a moment while I bring up the example. Okay, so here's one where the integral actually comes out to be something not terrible. And by not terrible, I mean actually doable without having to mess around with any of our really complicated trig expressions or anything like that. So let's suppose that we want to find the arc length of y is equal to x to the 3/2 from x equals 1 to x equals 2. Well, dy by dx, this is going to be 3/2 x to the 1/2 power. And therefore, my arc length is going to be the integral from 1 up to 2, square root of 1 plus 3/2 x to the 1/2 squared dx. This is going to give me the integral from 1 up to 2, square root of 1 plus 9/4 x dx. Now, the reason this is nice is because this turns out to be linear in x inside of the square root. But this I can do using a U-substitution. Sorry, I erased that without warning you. If you need to, rewind a bit, pause, and write that stuff down, because I got to have some more room to actually work out this integral. So this integral is going to, I want to do the U-substitution of u is equal to 1 plus 9/4 x, then du is 9/4 dx, so dx is 4/9 du. This is going to become the integral of 1 plus 9/4 is 13/4, 2 plus 9/4 is 17/4, and then we're going to have u to the 1/2 times 4/9 du. That's going to be 2/3 u to the 3/2, and then we also have a factor of 4/9, and then that's going to be evaluated from 13 over 4 up to 17 over 4. So there we go. I'm not going to actually finish this out. At this point, I trust you guys to be able to multiply fractions and evaluate things. Okay, so we're not going to like literally finish out every single step there. But we could do this integral very easily. Now, I believe if we set this problem up in the other way, if we did it over y, you would see that we get something much, much worse. But it turns out the two integrals are actually equal to each other. So what would we do if we had done the integral over y? Well, remember, our curve was y equals x to the 3/2 from x equals 1 to 2. Well, this means x is equal to y to the 2/3 from y equals 1 to y equals 2 to the 3/2 is the square root of 8. So 1 to the 3/2 is 1, and 2 to the 3/2 is square root 8. Sorry, I don't know why my brain hiccuped there as I was trying to figure out the bounds for y. But there we go. Now, the problem here is that this is going to give me dx by dy is equal to 2 over 3 y to the minus 1/3. Well, the integral I get is going to be 1 to the square root of 8. Now, that's not too bad, okay? Square roots and the bounds, we don't like them, but not a major problem or anything. In principle, we can certainly deal with it. But then we're going to have this square root of 4 over 9 y to the minus 2/3 plus 1 dy. Now, frankly, I'm not sure how to do this problem. I might be able to figure it out if I spent a while working on it, but I honestly don't know what the answer is in terms of finding that antiderivative. And I don't think it's obvious to anybody. Maybe it's obvious to one of you. If it's obvious to one of you, let me know, and I'll be like, wow, that's amazing. But like, it is not obvious how to do this antiderivative. And so you see how one form could end up being really, really nice, like the one that we just did, where we got it with a simple U-substitution, and the other format could be something really ugly that, honestly, I don't even know what I would do with this thing, okay? So, this is why it is so important to have both methods available to you. The method where you integrate over dx and the method where you integrate over dy, because one of them might be a fairly straightforward integral. You will almost never get like a trivial integral, okay? These arc length problems are pretty much always going to be something annoying. But you'll get one, hopefully, that is reasonably straightforward with techniques from Chapter 7. The other one might be something that, even with the techniques we've got from Chapter 7, we just look at this thing and we're like, I have no idea. We would have to spend an hour trying different things, and there's no guarantee that they would work. So there we go. That is our arc length stuff for you for today. So I'm going to stop here and let you guys spend some time thinking about this. I really want you to take a look at the examples in Paul's math notes. So you guys have a link to that, and I will post another one this week specifically to his stuff on arc lengths. But I really want you to look at some of those examples, and I may go over some of his examples in another lecture here, but seeing those examples written down, I think, is going to be more useful for you than just seeing me sketching stuff on this little tiny whiteboard. So yeah, we're going to kind of leave things there for the moment. We'll maybe do a few more examples of this stuff next time. We'll see how time goes. But in the meantime, the idea behind the arc length, fortunately, what I want to say is that writing down the integral is usually kind of not too bad to do as long as you understand where those integrals come from. And remember the formulas. It's solving the integrals that can sometimes get a bit finicky. And as I've shown you, one of the solutions is remember that there's alternate approaches to the problem and try the one that works the best for that particular problem. Don't necessarily assume that the way the problem is written down is going to be the easiest way to do it. You may need to, instead of having y written in terms of x, you may want to write x in terms of y and do the integral over dy if that gives you a much simpler integral. So it just kind of depends on what the problem says. And yeah, so this is again going to be one of those things where, you practice it for a while, it gets easier as you go. But again, the good news is that, I don't mind if you look up integrals in an integral table for these types of things, because I think when you're doing a lot of these problems, they're long enough and difficult enough as it is that I don't feel like that's really a bad thing to do. Anyway, we will be returning shortly with more applications of integration stuff.